Hello everyone, and welcome to the series on single variable calculus, where we're primarily going to be focusing on functions of a single variable or relations of two variables and sort of how those relate to each other, change over time, accumulate, and several other concepts and topics. Before we can jump into the realm of single variable calculus, we first have to answer exactly what we're going to be talking about, i.e., to some degree answer the question, what is calculus? So here are a couple answers that you probably would get if you were to ask someone who has already taken calculus exactly what is calculus about. A lot of people will actually say that calculus is about two objects known as derivatives and integrals. To some degree, they are not wrong, because often when calculus is taught, in particular single variable calculus, calculus 1 is commonly focused on taking derivatives of functions, which is just operations and transformations of functions, and also integrals of functions as well, which commonly take one of two forms, which we'll talk about later. Although derivatives and integrals are a crucial part of calculus education, they're not exactly the only things that you talk about in calculus. Therefore, to some degree, this first answer is probably the worst of these four answers. The next answer on this list that probably is a better answer would be the study of what we call limits. And limits, again, is another analytical tool or analysis method performed on functions and relations that can be used to define and describe derivatives and integrals. And limits can be used for other things aside from derivatives and integrals. Therefore, if somebody says the study of limits, technically that's a better answer than just saying the study of derivatives and integrals. Now, another way that people usually use to describe calculus is from the applicational or applied perspective, and they say that calculus is the study of change and accumulation. So in this sort of table, derivatives are one way to model change, and integrals are one way to model accumulation, but of course they are not the only ways. So, from the applied perspective, the study of change and accumulation is also a good starting point as well. But obviously, calculus is going to be a lot more than just change and accumulation. Now, at least in the origins of single variable calculus and just calculus in general, Newton, which was one of the founders of calculus, approached this from the perspective of the study of infinitesimals, which are things that are very, very small, and the study of infinites, which are very, very large. Right, and one can show that the derivative can be represented from the perspective of infinitesimals. Integrals can be represented from the perspective of infinites and also infinitesimals as well. But infinitesimals and infinites can be used for practically everything, and in some sense everything, in the realm of calculus. So to some degree, the study of infinitesimals and infinites would be the best answer one could define. But of course, since infinitesimals and infinites are a bit abstract, sometimes it's useful to sort of get a more applied and hands-on feel for what's going on in the realm of calculus, which is why a lot of people usually start with limits and then they go into derivatives and integrals, then they go into applications into, for example, studies of change and accumulation. And once they have a more rigorous understanding of what actually we're doing, then one can dive deeper into the study of what calculus actually is and study more in depth of what an infinitesimal and an infinite actually is and what their purposes are. The first type of problem that I want to look into today that calculus definitely does spend a lot of time developing is what is referred to as limits of functions, which we're going to define and explore a little bit more in detail a little bit later on. But as a guiding example, let's consider the function defined by sine x over x. One can easily see that the sine function is a well-behaved function. Literally, you could plug in any value into the value of x, and the sine of x will be defined. And obviously, that's sitting on top of the simple rational function 1 divided by x, which only has an issue when x is equal to 0, for which it has a vertical asymptote. So one could choose as the largest possible real subset domain for this particular function f to be the set of all real numbers except for x is equal to 0. Now, is it possible to extend this domain to something larger? In particular, is it possible to extend this to the entire set of real numbers and not exclude 0? Well, one thing we can begin to do to sort of analyze what this function is doing is to graph it. So if one were to construct the graph of the function sine x divided by x, one would actually see that the graph sort of looks like a sine wave, but it sort of dampens and disappears as x approaches plus or minus infinity, but there obviously should be an open circle when x is equal to 0 because it's not defined there. But you should be able to see, at least from the graph, if I were not to draw that open circle there, and obviously that circle is infinitesimally small, regardless of how many times you finitely zoom into that, you're never actually going to see that gap. Right? So to some degree, at least to the naked eye, this function looks like it doesn't have any issues from the graphical perspective. So one could ask, okay, well, as x gets close to 0 from either direction, what exactly is that value, y, for which we're actually approaching from the left and the right in terms of x is equal to 0? So one thing we see is that this function actually is an even function. So what do we mean by an even function? So if you don't already know what an even function is, keep in mind an even function is one whose graph is symmetric about the x-axis. In particular, if you choose a point over here, let's say minus x, and it has a particular y value, the associated positive x value has the same exact y value as its negative domain correspondent. So if a function is an even function, that means f of minus x must be equal to f of x for all values x inside of the domain of that particular function of interest. So if we use this particular function as a guiding example and evaluate this at minus x, what will we get? Well, that's just going to be equal to the sine of minus x divided by minus x. You should know that the sine of x is an odd function, so the sine of x sort of looks like this. So if we were to choose, for example, a minus x value and get a y value and choose its opposite correspondent in its domain, the y value is going to have the opposite value compared to its opposite component in its domain. Right? So that means the sine of minus x will be equal to the opposite of the sine of positive x, and obviously minus x is the same as minus x. But notice that these two negatives will cancel when we divide, so this is obviously equal to the sine of x divided by x, which is the same thing as the definition of f of x. So regardless of the x value for which we have chosen, we have that f of minus x is equal to x, implying that f is an even function. So why do we care about that this function is an even function? Therefore, as x approaches 0 from the left-hand side, it will be approaching the same exact value as it would from the right-hand side, since it is symmetric about the y-axis, right? So if we're interested in figuring out what this function is approaching as x gets close to 0, we only have to consider what x approaches 0 from only one side, because the other side is going to have practically the same symmetric behavior. So what we're going to do is we're going to plug in a bunch of numbers near 0 and get closer to 0 from one of these sides and sort of see what the y values get closer to. So what I'm going to do is I'm just going to make a little table of values here. So x on the left and sine x on the right. And let's choose a number that's quite far from 0. In particular, let's just choose 0.5, and then let's choose 0.1, and then let's get closer to 0.01, and let's get closer to 0.12341. Right? So obviously, as x gets closer and closer to 0 from the right-hand side, which will dictate by 0 plus sign, obviously these sign values should be getting closer and closer to something. But what are they getting closer to? So if you plug in 0.5 into sine of x, where x is typically measured in radians, you will find that this is going to be approximately equal to 0.9589. If you plug 0.1, and this should be sine x over x, by the way, and you plug 0.1 into this function, you're going to have that that's approximately equal to 0.9983. So it appears to be increasing, right? And the graph definitely indicates that as well. If we plug in 0.01, one can find that that's going to be approximately equal to 0.99998, right? Which appears to be getting closer to 1, so let's obviously do the last one and see what's going here. And if we plug in 0.00001 into sine x over x, we're going to get 0.123456789 nines followed by an 8. Right? So obviously it appears to be getting closer and closer to 1. So let's write this down. So it appears that as x gets closer and closer to 0 from the right hand side, and you can say that, okay, what is f of 0 plus epsilon, where epsilon is an arbitrarily small but positive number. So epsilon is arbitrarily small but positive. Right? And when I say arbitrarily small, I mean regardless of the smallness of this x value you've chosen, epsilon is going to be smaller than it. So epsilon is that concept of an infinitesimal, right? What value do we appear to be getting close to? Well, according to this table, that should be getting closer and closer to 1. And one can actually prove with some algebra that the value is exactly equal to 1 as you do arbitrarily get close to this number. So, if we were to sort of fix the issue of this graph, because we already know that this function sine x over x has a hole at x is equal to 0, if we want to make the domain equal to all real numbers and have this function be beautiful, we can define this function to be equal to 1 at x is equal to 0. Right? And now this function doesn't appear to have any holes or issues, and in some sense this curve is what we call simply connected or continuous. That is, we don't have to lift up our pen or pencil in order to draw this graph. So, if the original curve was sine x over x, and this new curve with this blue dot sort of filling in that hole of an issue, maybe this curve has a new name since it's a lot nicer than the original, and indeed it does. This function is what we refer to as the sinc function or the complementary sine function, and this is defined to be equal to the sine x over x for x is not equal to 0, and 1 for x is equal to 0. So what does this sinc function look like? So if we were to graph it, it would look exactly like the sine x over x function. The only difference is that this function doesn't have a hole, and therefore it doesn't have any domain issues. Therefore, we can clearly see that the domain of the sinc function is going to be all real numbers. The next problem that we're going to look at is targeted more on the application of the study of change. Let's consider the graph of an arbitrary function that doesn't appear to have any issues, in particular this one. Let's call this function f. Let's assume that this is the x-axis and this is the y-axis, which is typically assumed. Let's choose a particular point, for example this point. Let's assume that that is the point x is equal to a, and let's just choose a point in the future. Let's call that x is equal to b. And let's consider the slope of the line that passes through these 2 points, which some people refer to as a secant line. The secant line obviously is going to have some slope m, and let's assume that that's actually not what the purpose or goal of this exercise is. Let's assume that we actually just want the slope of the line that touches this function f at exactly the point when x is equal to a, and no point locally to that point, which we typically refer to as a tangent line. So this pink line is called a secant line, and this green line is called a tangent line. Right? So the secant line passes through the point when x is equal to a and b, and locally the tangent line only passes through the function f when x is equal to a and a only. So what is the slope of this particular tangent line with respect to m? Well, according to this graph, both are increasing, but m is a little bit more less in terms of magnitude compared to the pink m, right? So obviously we see that the slope in this graph is positive, therefore the function is increasing. So f is increasing when x is equal to a. But how fast is it increasing? I.e., what is that value of that slope? Well, for the slope of the secant line, we actually know a way to calculate that, right? So the slope for that secant line can be found by doing the average rate of change of the function on that particular interval, which we should already know to be equal to f of b minus f of a, all divided by b minus a. So for this particular function, one can say that, okay, the slope of that secant line is equal to the average rate of change, and this can be used as an approximation for the slope of that tangent line. Now, how can we make that approximation a little bit better? Well, obviously, if we choose a point on the domain that's a little bit closer to A, let's call it, for example, x is equal to c, and consider the slope of that line, notice that that blue line slope is a little bit more closer to that green line slope. Therefore, what we can do is we can just make the distance between A and B arbitrarily small, and let's call that again epsilon, and make epsilon get closer and closer to 0. To get a more conceptual understanding of what's going on here, let's choose a particular example to sort of illustrate how to do this numerically, if you had a function to sort of play with. So the example that I'm going to choose is just going to be a simple one. Let's choose a nice quadratic function, say x squared minus 7x plus 5. So one should be able to graph this if one can locate, for example, the vertex, the x-axis of symmetry, potentially even the x-intercepts if they exist, and moreover the y-intercept, which we know to be equal to 0, 5. So let's assume our goal is to answer the question, how is f changing when x is equal to 2? That is f increasing when x is equal to 2? Is f decreasing when x is equal to 2? Or does f, for example, have a maximum or minimum when x is equal to 2? Or something else? So, if we were to graph this out, let's just do a quick sketch just to get an idea. One can show that the vertex of this parabola is located at about 3.5. And since the vertical intercept is located at 0, 5, then this parabola is going to sort of look like this. And let's assume that that is our vertex. So if we look at, for example, when x is equal to 2, x is equal to 2 is going to be located there. And if we draw a tangent line to the curve at that point, let's assume that that is a tangent line, not a secant line. Obviously, this slope is negative, and hence the function should be decreasing. But how fast is it decreasing? So what we can do is, for example, find the slope of the secant line, for example, at a point in the future, say across 2, 3, use that approximation, and then make this number that we've chosen get closer and closer to 0. So instead of choosing 3, we can choose like 2.5, 2.1, 2.01, 2.0001, and so on. So let's just calculate a couple average rate of change to approximate that slope of that tangent line. So the average rate of change of f on the interval 2, 3, we know is just going to be equal to f of 3 minus f of 2, all divided by 3 minus 2. If you just plug in these points 3 and 2 into that function, you're going to get minus 7 minus negative 5 divided by the bottom, which is 3 minus 2, and one can find that that's going to be equal to negative 2 divided by 1, which is going to be equal to minus 2, which is obviously decreasing. But we already know that it's likely that the slope of the secant line and the slope of the tangent line are very, very different. Therefore, it's important that we make this number as close to 2 as possible, which we can easily do. So obviously negative 2 is an approximation, but it's obviously not going to be the best one. So let's get a little bit closer to our domain point of interest. So the average rate of change of the function f on the interval 2 and 2.1, one can find to be approximately equal to minus 2.9. The average rate of change of the function on the interval 2 and 2.01 is approximately equal to minus 2.99. And let's actually draw or write average rate of change of 2 on the interval 3, just to remember sort of where we're coming from. So we're at minus 2, minus 2.9, minus 2.99, and one can find that the average rate of change of f on the interval 2 and 2.12341 is approximately equal to minus 2.1234 and 5. Not 5, but 5 nines. There we go. So what do you see? What do you observe when we get closer and closer to 2, obviously from the right-hand side? So notice that for 2 and 2 plus epsilon, that interval, the average rate of change of the function f is getting closer and closer to -3 as epsilon gets closer and closer to 0 from the right-hand side. And notice that we're pretty much working with the same exact concept. As we get closer and closer to something, what is the object of interest getting closer and closer to? And this is the rudimentary element behind what is called derivatives, which we'll definitely spend a lot of time on a little bit later on. The last problem that we're going to be looking at today is on the other side of the study of calculus. Instead of the average rate of change for studying change, now we're going to be looking at the study of accumulation, which is where integrals are going to be obviously used in practice, at least in some part. So let's assume that we have, again, some particular curve here. Let's actually choose a nice curve that we're familiar with. For example, f of x is equal to x squared, where the horizontal is x and the vertical is y as usual. And let's assume the interval 1 to 3. And let's assume we can consider the area underneath that curve. So a natural question is, what is this area equal to? Now obviously one could look at this shape and be like, well, it sort of looks like a trapezoid, but the side of this trapezoid is slightly curved. So one can say, well, maybe I can approximate it with a trapezoid or some object, right? And you definitely could. But how good would that approximation be? And possibly, if you don't remember the area of a trapezoid, maybe a trapezoid is too complicated of a shape to work with. So one easy shape that we can actually do is to consider rectangles, because most people do know the area of a rectangle. That's just going to be equal to length times width, or length times height. So what I'm going to do is I'm going to partition this particular area into two pieces. I'm going to consider the interval 1 to 2 and the interval 2 to 3. That is, I'm partitioning, so I'm going to partition the interval 1, 3 into 1 and 2. Let's do 1 and 2. Union 2 and 3. Notice I'm not including the right endpoints here, and obviously you should be including 3 there, so everything is considered. But notice I'm focusing mainly on the left endpoints, right? So this is going to be a left endpoint focus. And the reason I want to focus on the endpoints here, the left endpoints in particular, is because I'm going to be building rectangles based upon those left endpoints. So in this particular picture, my left endpoint for the interval 1, 2 is going to be this orange rectangle here, and the left endpoint for the interval 2, 3 is going to be this rectangle here. Notice that I'm focusing on the left endpoint for these particular rectangles, not the right, based on my focus, but of course you could use the right endpoint as a focus, and that is perfectly okay, especially for this example, or you could even use the midpoint or possibly even trapezoids on each of these subintervals. So with this in place, let's see if we can approximate this area based upon this rectangle approximation. Obviously it's not going to be super ideal, but it's going to be a starting point at least. So let's draw our curve here again, and let's draw our interval 1, 2, and 3. So this is going to be our rectangular approximation. Obviously we see from the graph that since this function is an increasing function always on the interval 0 to infinity, if we use left endpoint rectangles, we're always going to have an under approximation for this particular area. If you were to use right endpoint rectangles, since this function is increasing, that approximation will always be an over approximation. So midpoints would obviously just be the average of the left and the right, and that would possibly give you a better approximation on average. But what's the height of each of these left endpoint rectangles? So if this is the function f, then that means the height of this first rectangle is going to be f of that particular left endpoint, which is going to be 1, and the height of this next rectangle is going to be associated to that left endpoint domain value, which is going to be f of 2. So that means this area approximation with n is equal to 2 rectangles is going to be equal to the distance here, which is 1, times the height of that rectangle, which is f of 1, and then plus the length of the next rectangle, which is 1, and the height of the next rectangle, which is going to be f of 2. Notice that the length of each of these rectangles is the same exact one. So this is what we call a uniform distribution or a uniform partition. So if it is a uniform partition, it's quite easily to find the area of these rectangles. Because these lengths are all going to be equal, therefore we can always factor that out. And then what we have inside of this bracket is just a sum of function evaluations. So if we plug in, for example, f of 1, that's going to be equal to 1 squared, which is 1, 2 squared, which is 4, which is going to be 1 times 5, which is equal to 5. So 5, in this case, is going to be an under approximation for the exact area. So let's see if we can get a little bit more accurate in terms of this approximation. So what is f of 4 going to be equal to? So what we're going to do is we're going to be taking the same interval, 1, 2, 3, and then we're going to be breaking it into 4 pieces now. So this is now going to be 1.5 and 2.5. Now the question becomes, what is the length of each of these uniform subintervals, right? And let's call that length, for example, delta x. Well, delta x is obviously breaking up the range 1 to 3, which has a total distance of 3 minus 1, and we're breaking it up into n pieces. In this case, that's going to be equal to 4. So that's going to be 2 divided by 4, which is going to be 1/2, which is 0.5, which matches this particular picture. In general, delta x is always going to be equal to b minus a divided by m, where b is the upper bound, a is the lower bound, and n is the number of rectangles for which you are partitioning this area into, right? So that's for an n rectangle approximation. So if we use this formulation to find, for example, a4, then we're going to have a4 is going to be equal to 3 minus 1 divided by 4 times f evaluated at each of those left endpoint values. So that's going to be equal to f of 1 plus f of 1.5 plus f of 2 plus f of 2.5. Now let's see if we can generalize this just a bit more before we jump to the general case. So this is obviously going to be equal to our delta x term, and then this is going to be equal to f of 1 plus 0, and then this is going to be f of 1 plus 1 times our delta x value, because keep in mind delta x is 0.5, so that's going to be 0 delta x, 1 delta x, and then it's going to be 2 plus, or 1 plus 2 delta x, and then f of 1 plus 3 delta x's. Because 3 times delta x is going to be 1.5, and 1 plus 1.5 gives us our 2.5 that we started with. So once you have this approximation out, then you're going to have that we're going to have this approximation to be about 6.75. So A2 was equal to 5. A4 is 6.75. It's increasing, obviously, but increasing to what is the question. So obviously we would increase this up to something bigger. For example, 8 would be a good number. So we're going to have 3 minus 1 divided by 8 times f of 1 plus f of 1 plus 1 delta x, where delta x is now going to be 2/8 or 1/4, and then we're going to have f of 1 plus 2 delta x, and then we're going to extend this all the way out to the last one, which is going to be 8 minus 1, which is 7. So you may want to sort of spend some time with that to sort of convince you that that is going to be 7 times delta x at the very end, and one can see that that's going to be approximately equal to 7.6875. So it's obviously getting closer and closer to some number that appears to be less than 10 for sure, maybe less than 8, we don't know. But is it possible that we can easily generate a formula that will allow us to converge that number a little bit more quickly, right? So obviously, as n gets closer to infinity, this area approximation an is getting closer and closer to something, right? So if we look at the general formula for an, that's going to be equal to b minus a divided by m, which is obviously our delta x, times f of a plus 0 delta x plus f of a plus 1 delta x all the way out to plus f of a plus n minus 1 delta x. So this is obviously the left endpoint approximation, right? So let's just write that down. So a left endpoint area approximation with n uniform length rectangles. So that's what this AN stands for, that long statement. So one can find, at least in summation notation, if you're familiar with this, is going to be equal to b minus a, all divided by m, times the sum from k is equal to 0 to m minus 1 of f of plus a plus k delta x. Right? So that is our left endpoint area approximation with n uniform length rectangles. So if you have, for example, Desmos, then you can easily evaluate this for any value of n. For example, A100 is approximately equal to 8.59. A of 1000 is approximately equal to 8.6587. A of 100,000 is approximately equal to 8.66659. And you can be like, okay, well, what does it appear to be getting close to? Well, maybe it's getting close to 8.6666666 and so on, right? And indeed it is. So one can find approximately that AN is getting close to 8.6 repeated, which you should know is the same as 26 thirds. Right? That's the exact answer, and one can prove a little bit later on once we develop some tools that actually is our exact answer. So for all of these three problems that we've discussed, for example, measures of change, measures of accumulations, and measures as you get close to numbers for a particular domain value of a function, obviously there should be shorter ways to calculate these things, which is where a nice study of, algebraic and graphical limits, derivatives, and integrals obviously are going to come into play, and we will definitely spend some time on each of them. But for now, that's all I want to do in terms of introductions, so I'll see you in the next video where we start to talk about limits in a little bit more detail. Hope to see you there, and I hope you enjoyed this video. Take care.